So based on what we just saw in the previous slides, remember that the z-score that we inserted into the Gaussian probability density function allows us to calculate the probability of obtaining a z-score, between negative 1.96 and positive 1.96 is equal to 0.95 or 95%, 95% of the time. The difference, which is 5%, is split over two tails, on the left tail and on the right tail. And this is important because this will represent the 5% or 0.05 significance. Let's come back to testing the null hypothesis. So as we saw in the z-score, we have the difference between the sample means, and now we want to test it against the null hypothesis, which in this case will be the difference between the hypothesized population means, and because we want to show that there's no difference, these two theoretical population means will be the same and therefore equal to 0. So then your numerator remains the difference between your sample means. In the denominator is your standard error, the standard error of the difference between two independent sample means. Now, when we look at this z-score, remember the three questions, or 3 of the 7 questions we talked about, and the first was, how large is the mean difference between groups? So this is in your numerator. Perfect. How many patients were in each group is going to affect your denominator. And how large is the variation in response among patients is also going to affect your denominator. Now, because we don't know the population or theoretical variance of the difference, we need to replace it by the sample variance. And this is why when you ask how many patients were in their group, it's going to have an effect, because the larger your sample, the more this term will be minimized, which is a good thing. It's reducing your noise. And when we ask how large is the variation in response among patients, once again, the larger this variation, the larger this term, and therefore the more your noise, which is not a good thing. And so what you want to do is maximize your signal while minimizing this term, which is by making, or by hoping for a smaller variation in response among your patients, and using as large a sample size as possible. So in the late 1800s, early 1900s, a mathematician, William Seeley Gossett, who worked for Guinness Beer, was struggling a little bit with the application of the Gaussian curve, the central limit theorem, and the z-score for his testing. You know, he was responsible for quality control, and he needed to be able to test his product. And so when he applied his work, his analyses, to smaller samples, he realized that the curve didn't look quite the same. And basically it was flatter, so the peak was lower, and wider tails. So that when you looked at the cut point, so you see here on this graph, the red line is the standard normal curve, with here the plus 1.96 cut point, which leaves 0.025 in the tail, is going to be problematic for the curves he was getting for smaller sample size. So for example, here this is for a sample of 5, which is very small. But if you use the same cut point, the percent area in the tail is going to be much greater. And you realize, whoa, that's a problem. And he wants to work with small sample sizes because in his work at Guinness, he just couldn't justify sampling very large samples all the time to get an estimate, as well as he realized he doesn't know the theoretical value of the variance of the population. And so what he did is he derived what's now called the student T. He had to publish his work under student because he was working for Guinness, and he didn't want people to know that he was publishing his work. He didn't want Guinness to know he was publishing his work, so he published under student, you know, as a mathematician named student. Let's have a look at this student t-test. Well, at first glance, it certainly looks like it's very similar to the Z ratio, which we just looked at. And that's because we have the difference between the sample means. We're then comparing to the null hypothesis, which is the difference between the population means, and we are assuming the two are the same, and therefore it will be equal to 0 and it will drop out. And we previously divided by the standard error of the difference. And the standard error in the Z ratio, we use 2 times the variance, or square root of 2 times the variance of the population, because we're making the assumption that the two populations are the same. In this case, because Gossett was interested in working with small samples, we are using the pooled variance here in order to get the standard error. And the pooled variance, you'll see the equation here, don't worry about it, but basically it simplifies to what looks like the average of the two variances from your samples. So, and you take the square root of that, and that gives you your standard error, because don't forget we're dealing with means here. We're dealing with repeated sampling, so many means, which when you take the standard deviation of the variance of means, you end up with the standard error. When you use this standard error in the t ratio, you're going to get a very similar result from the Z ratio. However, what is going to differ are the cut points. And let's have a look at that in the next slide. Now what we're doing in this slide is explaining why Gossett chose to develop the student t-test instead of just using the Z ratio. Now, as we explained earlier, what Gossett observed was that for his small sample sizes, the distribution, the probability distribution, was flatter with wider tails. And what this does essentially is when we use the standard 1.96 cut points for our Z ratio, which is supposed to result in 95% of the distribution with 5% on the tails, so that's 2.5% on each tail, that with the small samples, there would be an overestimate in the area on the tails, meaning it would be greater than 5%, because the curve is flattened with wider tails. And so this data here shows this. So what we're doing here is we're taking both tails, we're putting them together using the 1.96 cut point from the Z ratio, but we're applying it to data sets that are very small. Sorry, not data sets that are very small, to sample sizes that are very small. And so you can see here immediately when you have a very small sample size of 3, and using the 1.96 cut point for the Z ratio, that the area on to the right and to the left of the tails of the cut points is much greater than what's expected, which is 5%. You can see here we're getting, a good 12%. As you go up in sample size, the area to the right and left of the cut points is starting to get smaller. So meaning that it's approaching what we had hoped with the Z ratio for obtaining or expecting, which is 5%. So you see here already at 61, we're really close to the 5% cut point. When we get to 100, we're even closer. And so inevitably, as the sample size increases, we approach the Z ratio probabilities from these cut points. So what did Gossett do? Well, essentially, he just said, well, what I'm going to do is I'm going to set different cut points for each sample size. And he does this by the degrees of freedom, which I'm sure you heard of, and we'll probably talk about and define the degrees of freedom later in the course. But essentially what the degrees of freedom are doing is setting the sample size and the appropriate cut points for that sample size in order to observe the 5% in the areas outside the cut points. And by doing this, he's now developed a test, so the student t-test, that allows you to compare and test just like the Z test does, but using the sample variance, because we don't know the theoretical variance of the population, and allowing for smaller sample sizes. Okay, let's move on to the last 4 questions. Now let's just recall them. How large is the mean diastolic blood pressure difference between groups? So now we're asking, how big is the difference? How big is the signal? How many patients were in each group? So this is a sample size question that we need to address, which we're just beginning to do so when discussing the t-test. How large is the variation in response among patients? So this is the variability within the data set that we need to be concerned with. And finally, are the 2 groups comparable? Now, before we jump in to these 4 questions, let us consider a few important statistical summaries just to build your statistical base, so to speak. Let's start with a common summary statistic, the measure of location. In general, the measure of location is used in order to identify the center of your distribution. For example, if we use this small data set of 5 values, we could order these values in ascending order, assign them a rank, and then look for the center rank, the middle rank. And in this case, because we have 5 values, the middle rank will be 3. And assigned to this middle rank is the value 9, and therefore our median is 9. We could also calculate the sample mean, which is, as you know, is just the sum of the values divided by the number of values in the data set. And in this case, it's equal to 12. And so when the median and the mean are not equal, this is an indication that your data is not distributed normally. There is another measure of location, which is called the mode, and this one is not used very frequently, and it just represents that value in your data set that has the highest frequency. Let's have a look at some summary statistics of variation. So if we go back to our data set from the previous slide, and we keep it in ascending order, it is easy to identify the minimum, the maximum, the range, which is simply the difference between the minimum and the maximum, which is 22 minus 4 is 18. If we then consider the ranking of the data, if you remember correctly, the center of the data, which was the median and was 9, is now going to become the second quartile. So the median represents the second quartile. The first quartile in this case, because the data set is so simple, the first quartile is here at 7. The third quartile will be here at 18. And the interquartile range is very simply going to be the difference between your first and third quartile, which is 18 minus 7 and equal to 11. Let's consider another measure of variation, but this time we're interested in the spread of the data from the center of the distribution. So one way we could consider would be the mean of the deviations about the sample mean. So you can see here in these calculations that we're simply taking the difference of each data point from its mean, and then we just divide it by the number of data points. The problem with this one is that it's always equal to 0. So this is not really a useful measure of anything. How about if we were to take the mean of the absolute deviations about the sample mean? So this way we're certain, or pretty certain, that we're not going to get 0 as an answer. Now I think we're getting close, but we're not quite there yet. Okay, how about if we take the mean of the squared deviations about the sample mean? Well, if we do that, we've got the formula for the sample variance. And by taking the squared deviations about the sample mean, summing them all, and dividing by the size of the sample minus 1, we get an unbiased estimate of the population variance. So you can say, why do we need to divide by n minus 1? Well, when you think of it, if you were to randomly draw a value from a distribution, the probability of you drawing the mean or a value close to the mean is higher than drawing a value in the tails. And that just makes sense. So if you have a very small sample, then the chances are that small sample is going to be comprised of values close to the mean. And if you calculate your variance based on those values, the estimate of the variance of your population is going to be underestimated. And in order to help with that, you divide by n minus 1. Because by dividing by n minus 1, you reduce your denominator, and therefore you're compensating for your numerator being an underestimate. As your sample size increases, so does your variance in your numerator, and dividing by n minus 1 has very little effect. Just think of it. If you divide by 5 minus 1, which is 4, that's a big change. Whereas if you were to divide by 100 minus 1, which is 99, that is a small change. Anyway, that's what results in an unbiased estimator, and we are going to move on. Now here's an interesting observation. What if when we did the least squares calculations, instead of using the mean, which was 20, we used 22? Well, when you calculate your sample variance, you'll notice that it will always be greater than if you had used the sample mean in the calculation. And so the sum of squares deviations is minimized when the square deviations are about the sample mean. And it's for this reason that we call the sample mean the least squares estimator. And this will come in handy when we start talking about regression. More on that in future lectures.